What is an Indian? Say detailed engineering? Have you ever stopped to think about what makes it possible for your smartphone screen to respond to touch so precisely? Or how state-of-the-art solar panels convert sunlight into electrical energy? Behind these everyday technologies is an unsung hero, indium. This rare and versatile metal, often overlooked by the general public, has extraordinary properties that have revolutionized modern industry. Its journey from its accidental discovery in a German laboratory to cutting-edge applications in nanotechnology reveals a fascinating story of scientific innovation and geopolitical challenges. But first, what exactly is indium, chemically classified as a post-transition metal? Indium, with the symbol in an atomic number 49, is part of group 13. Along with aluminum, gallium, and thallium physically, it appears as a soft and malleable metal with a characteristic silvery white color that resembles polished silver. Its name comes from the indigo or blue-violet spectral line observed during its identification in 1863, a tribute to its luminous signature in the electromagnetic spectrum, with an abundance in the Earth's crust estimated at only 0.1 parts per million. Indium is considered one of the rarest metals on Earth, scarcer than silver or mercury. And how was it discovered? The discovery of indium is a fascinating chapter in the history of chemistry, marked by happy accidents and scientific insight. It all started in 1863. It began in the mines of Freiberg, Germany, where the chemists Ferdinand Reich and Hieronymus Theodor Richter were investigating zinc ores in search of traces of thallium. When performing spectroscopy tests, a then revolutionary technique that analyzes the light emitted by heated materials, they detected a bright indigo blue line. Never before documented, this unexpected spectral signature revealed the presence of a new element. After 4 years of meticulous experimentation, Richter managed to isolate the metal through hydrolysis of its salts, marking the official birth of indium as a recognized chemical element. Interestingly, the initial purity was so low that the first samples resembled a dark powder more than the silvery metal we know today. And what are the properties of indium? Which physico-chemical properties of indium explain why it has become irreplaceable in modern engineering? Chemically, it behaves as a relatively stable metal under ambient conditions, but it shows interesting reactivity when heated or combined. When exposed to air, it forms a protective film of indium oxide, which prevents deeper corrosion. However, when heated above 200 degrees Celsius, it oxidizes vigorously, producing a bluish flame. Physically, it is notable for its exceptionally low melting point of 156.6 degrees Celsius, which allows its use in special solders that do not damage sensitive electronic components. Another peculiarity is its record-breaking ductility, which allows it to be rolled into extremely thin sheets of just 0.01 millimeters thick, a crucial property for transparent coatings on screens. Materials engineers are also well aware of its characteristic squeak, where, when bent, it emits a high-pitched sound due to intercrystalline friction, a rare phenomenon among metals. The origin and extraction of indium present a complex geological and industrial challenge wherever it is found. Unlike metals like gold or copper, indium hardly forms deposits of its own minerals. It occurs as a byproduct of mining zinc, lead, tin, and copper, present in concentrations that rarely exceed 100 parts per million in the host ores. Geographically, the largest reserves are concentrated in China, which is responsible for about 60% of global production, followed by South Korea, Japan, Canada, and Peru. The extraction process begins at zinc smelters, where the ore undergoes leaching with concentrated sulfuric acid, dissolving valuable metals. In this acidic solution, indium is separated through selective precipitation by adding powdered metallic zinc, which reduces lithium ions to their metallic form. The residue then goes through electrolysis in a sulfate solution, producing crude indium with 99% purity. The final stage involves sophisticated refining techniques, such as zone refining, which raises the purity to an impressive 99.99%. Essential for electronic applications, indium's uses in engineering show how a little-known element has transformed everyday technologies. The undisputed star is indium tin oxide, a material that consumes about 70% of global production. This conductive ceramic combines two seemingly contradictory properties: high optical transparency and excellent electrical conductivity. In touchscreen displays, this oxide forms nanometric films that detect touches with millimeter precision, while allowing light to pass through in next-generation photovoltaic solar panels. The coating of this oxide maximizes light capture and minimizes reflections. Aerospace engineering uses indium lead alloys in special solders to join critical turbine components, taking advantage of their low melting point, which prevents thermal damage. In the nuclear industry, the isotope indium-115 is an essential component of control rods in reactors, where its ability to absorb neutrons helps regulate chain reactions. A lesser-known but vital case is the use of anti-corrosive coatings for aviation engine bearings, where extremely thin layers of indium reduce friction and prevent catastrophic failures. Infrared sensors in medical and military equipment also rely on indium antimonide crystals, which are capable of detecting minimal thermal variations. The challenges and future prospects of indium reflect tensions between technological innovation and sustainability, as it is classified as a critical element by the European Union and the United States. It faces a crisis of availability, with estimates suggesting that economically viable reserves will last less than 20 years. At the current rate of consumption, which is growing by about 8% per year, the concentration of production in China creates geopolitical vulnerabilities in the global supply chain. To address this scenario, two fronts are becoming urgent. Advanced recycling has become an industrial priority, with hydrometallurgical techniques that recover up to 60% of the indium contained in discarded screens, a process that starts with shredding, followed by treatment with acids and selective solvents. At the same time, laboratories around the world are searching for alternatives to indium tin oxide, testing silver nanowires, doped graphene films, and modified zinc oxides. However, no material to date has matched the unique combination of transparency, conductivity, and durability of indium tin oxide. Innovative projects are even exploring the use of indium in solid-state batteries and flexible electronics, where its exceptional mechanical properties open up new horizons. Its journey reveals how specific physical and physicochemical properties, such as common ductility and unique electronic behavior, can catalyze technological leaps. But they also serve as a warning, where rare metals like indium remind us that the planet's resources are finite. The future will require not only new applications, but a radical reinvention of how we extract, use, and recycle this extraordinary material. As the British chemist John Emsley aptly put it, in the periodic table there are no insignificant elements, only properties that have yet to be explored. If you enjoyed the video, please subscribe, like, and turn on notifications.